Okay, so part G is given the MZ values of these molecular ions and their relative intensities. Okay, so it's quite similar to the one we've just done. All right, so I'll do this briefly. We've got, looking at the first one, cypermethrin. We're given the formula, and so we could work out what the MR of that formula is, and that's going to come out to 416 using 35.5 for chlorine. Okay, but now what we might do is just consider the molecule minus its chlorine. All right, because we know that chlorine isotopes come in two shapes. Okay, so this chlorine, right, although it's going to average 71, we're going to have options here. So let's write the options here. It could be, this part of the molecule could be 70, right? It could be 72 when we've got two 35s, sorry, a 35 and a 37, or it could be 74 when we've got two 37s. All right, the first one of 70 is when we've got two 35s. In which case, our 416 is it's never actually 416, is it? So a molecule might have two 35s in it, in which case it's going to have an MZ of 415. The molecule might have one of each in there, in which case it's going to be 417, and it might have two 37s in there, in which case it's going to be 419. Right, and so that is the MZ values for the first one at least, and the relative intensities you work out, well, you just used them from the previous question, doing that probability work there, so I won't go through that again. And the other two molecules are quite similar, right? So, or at least we're going to do them in the same way. So we're looking at the formula here of the second one, delta methrin, which is exactly the same, I think, apart from it's got a couple of bromines instead of a couple of chlorines. All right, so with the formula, we could get the MR of the formula, and that's 505. Then we need to appreciate that bromine comes in two isotopes as well. All right, so you know from your periodic table that the MR of bromine is 79.9. The AR rather, and we're going to call that 80 because bromine comes in two isotopes, right? And they're pretty close to 50% each, right? So you get 79 bromine, and you get an 81 bromine. Now I've not read the question in detail, so it might tell you that in the early part of the question. If not, it's presuming you know that. Okay, so. You know that there's two isotopes of bromine and each one is 50-50, which I suppose is quite a stretch for you to know that if it doesn't tell you that. Anyway, using the same logic as we did in the first, we can work out that the options for the MZ are as follows. We could have two 79s, right, in the molecule, in which case this would be the bromine part of the molecule would be 158, or we could have we could have one of each. All right, we could have a 79 and 81, in which case the bromine part is going to be 160, or we could have two 81s, in which case the bromine part is going to be 162. In which case we just adjust the MR for those three cases that we've discussed, and you're going to use the same percentages here to work out the relative abundance of those three molecules. So I won't do that again because just use the same method as we had in the previous question. Lastly, let's have a quick look at tralomethrin. And this is a molecule slightly different, but we're going to treat it the same in exactly the same way. First of all, we're going to look at the formula and get the MR of the formula. That's 665. And then we're going to notice that we've actually got four bromines on the end of the molecule like that. All right, so you could have one version of this molecule that's got 4 of the 79 bromines. Right, so that's going to give you an MR of 661. Or you could have a molecule that's got 3 79 bromines and 1 81. Oops, right, and that's going to give you a molecule with an MR of 663, right? And you can, I've run out of space, but you could do the other options there as well to get all the options. And in the same way, you can work out the probabilities to give you the abundances. Okay, so hopefully that's helped you with part G as well.